What's up guys, it's me Sir Ernest, and today we're going to talk about how to read a potential energy curve. Now below is a graph of a one-dimensional potential energy function U, which is a function of your x. Okay, and let's say the energy of your particle within this field is in this level. So in this region, we can see that the particle can only be found from this point and beyond. So the particle is allowed to be here, and it is not allowed to be here. So we call this your forbidden region. Now from this figure, we can see that there are positions where the slope of this potential energy curve within this allowable region is 0. And here we identify them as this point. Let's call this x1. This point, let's call this x2, and let's say at this point or anywhere between here, let's call this x3. So at this point, the slope of the graph is 0. So what does it mean? So by definition, we already know that the force exerted on a particle is just equal to the negative derivative of the potential energy with respect to x. So by virtue of Newton's law, if this is equal to 0, therefore the particle is in equilibrium. We call this 3 points your equilibrium points. Okay, so that means a particle at positions x1, x2, and x3. Okay, the particle is at least moving with a constant velocity. They are either at rest or they're moving in a straight line with a constant speed. This is by virtue of Newton's first law. Now, for example, at x1, the particle is in equilibrium. So when the particle is moved, for example, to the left, so let's say here, let's call this XA. So you notice that the slope of the graph here is negative. By definition, again, f at XA is negative derivative respect to x. So that means the force will be positive. So we can write this as there is a force going to the right. So the particle, when it's placed at XA, the particle will just be pushed toward the equilibrium point x1. For example, the particle now moves to the right. Let's say at xb. So you will notice that at this point, the slope of the graph is positive. So f at xb, which is negative derivative of u with respect to x, so this becomes negative. So that means the direction is to the left. So the particle will also return to its equilibrium position. So that's why we called x1 as a stable equilibrium point. Because whether you place the particle to the left or to the right of x1, the particle will eventually return to x1. Now, on the other hand, let's say we consider point x2. Okay, and let's say the particle located at x2 is placed to the left, let's say at xb. So we already know that the force at xb, because the slope is positive, the force, which is negative derivative of u with respect to x, will be negative or to the left. So the particle, when from x2 is placed at xb, the particle will move away from x2. Similarly, if we place the particle, let's say to the right of x2, let's say that's xc, so the slope here would be negative, so the force will be to the right. So the force at xc, which is negative derivative of u with respect to x, is positive or to the right. So again, the particle will move away from your equilibrium position. So that's why we called x2 as an unstable equilibrium point. Now, another type of equilibrium is called a neutral equilibrium. This happens when a particle is what we call in a saddle point in the potential energy curve, and that is represented as x3. So you will notice that if the particle is moved to either to the right near to x3 or to the left, the particle will neither move away or toward the equilibrium position. So mathematically, we can calculate or we can identify whether a point is unstable, stable, or neutral by getting the second derivative of the potential energy with respect to x. So for a stable equilibrium, the second derivative of your potential energy curve must be greater than 0. For unstable, the second derivative of u with respect to x is negative. And lastly, for a neutral equilibrium point, the second derivative with respect to x of your potential energy is equal to 0. So by calculus, the second derivative of a curve basically tells us the curvature of your curve. So for a stable, this is curved up, the curvature is down. For an unstable, and there is no curvature for a neutral equilibrium point. Okay, so that's it. That's how you basically read a potential energy curve. And this is very useful, especially when you start working on reading these kinds of curves for electrostatics or electrodynamics, as well as in quantum mechanics. Okay, so that's all for now. Thank you guys for watching. I hope you learned something today, and I'll see you guys in the next video. Bye-bye.